Hello friends, welcome to another tutorial in digital signal processing series. In this tutorial we'll talk about discrete Fourier transform DFT. Let's look at the definition of DFT. It's a transform that converts one finite sequence of equally spaced samples of a function x of n into a same length sequence of equally spaced samples of the DTFT, which is a complex valued function of frequency. Now this definition is comprehensive in itself, but I've highlighted 2 points here. The first one is that it is going to be the transform with the same length of sequence. DFT is going to be the transform of a discrete signal, but the transform itself, x of k, will also be discrete in nature, and the length of k will be the same as that of the length of x of n. So let's look into more details of DFT mathematically. If we go from one domain to another domain, it is known as transformation. So we go from discrete time domain into discrete frequency domain, but the number of samples here in time domain are n, let us say, so the number of samples will also remain n here also. And the inverse is inverse discrete Fourier transform, that will take us back to x of n. And if you look at the mathematical formula, how can you calculate x of k? By the way, you'll need to calculate x of k for only those values of samples for which x of n is present. So that is how it is different from DTFT also. If you look at the formula here, you simply need to go from 0 to n minus 1, and where of course n is the total number of samples as mentioned here, and n and k will be equal. So you'll calculate k for only those values of sample for which n is present, and the formula is going from 0 to the maximum number of sample present, e raised to power minus j 2 pi n k upon capital N. Now that will be more clearer when we do a numerical. And by the way, you could also calculate x of k using another method which is known as the Twiddle factor or the Twiddle matrix method. You can find x of k by multiplying your x of n with wn and nk, where wn and k is Twiddle factor and its value is this. So I'll show you how you can do that. And the inverse discrete Fourier transform has this formula where it is 1 upon n. This is conjugate of Twiddle matrix y of k. Let's understand this with an example. So we need to compute a 4-point DFT of the sequence x of n, where x of n starts here. So this is going to be the origin. This is sample number 1, 2 and 3. So it goes up to sample number 3. It has 4 samples. So these are 2 different things, and we need to sketch the magnitude and phase spectrum of x of k. And we know that x of k will also be present for 0, 1, 2 and 3 samples from the previous discussion. So we'll calculate only x of k for 0, 1, 2 and 3, and we can do that using 2 different methods. The first one is the traditional method, where we use the formula for x of k that goes from 0 to n minus 1. The number of samples here are 4, so we'll go from 0 to 3, and e raised to power minus j 2 pi n k upon n, where n will also go from 0 to 3 in summation, and k will be put as 0, 1, 2 and 3 to find out the values of x of k. So that's how we do that. So putting the value of capital N to be equivalent to 4, we get x of k to be equivalent to summation n going from 0 to 3 x of n e raised to the power minus j 2 pi n k upon 2. This 2 is not there, and pi n k upon 2. So when we calculate x of 0, let us say for k is equal to 0, what we'll do is we'll substitute k as 0, so e0 will be there in each of these terms. And of course when we open this summation, so we get x of n at 0, x of n at 1, x of n at 2, x of n at 3 multiplied by e raised to the power 0, which will be x of n at 0 is 0, x of n at 1 is 1, and this is 2, and this is 3, all multiplied by 1. So this is going to be added. So this will result in summation of all the samples. So the value becomes 6. And similarly, when we put k is equal to 1, so by putting k is equal to 1, we get x of n. This term, by the way, becomes 0. X of n e raised to the power minus j pi 1 into 1 upon 2 e raised to the power j pi 2 into 1 upon 2. N varies from 0 to 3, you know that. So this is 2 into 3 upon 2. And by the way, this is going to be 1. There's this mistake here. Oh no, this n will be 3 and k will be 1. So this is 3 into 1 upon 2. So we get x of n is 1 into e raised to the power minus j pi by 2. X of n is 2 into e raised to the power minus j pi. So you can expand these e raised to the power j pi as Euler's formula. So cos of minus pi by 2 plus iota sine pi by 2, and so on. And you know the value of cos of minus pi by 2 is 0, and then minus j is left out of here, and then minus 2 plus 3j. So you get a complex valued x of k at 1. Similarly, for x of k is equal to 2, you get e raised to the power minus j pi plus 2 e raised to the power minus j 2 pi plus 3 e raised to the power minus j 3 pi, which will result in minus 2. So this part could look a little intimidating because of some tricky mathematics where you need to convert e into Euler's formula, where cos theta and sine theta values are needed to be known. And finally we get the value of k is equal to 3, again varying n from 0 to 1, keeping k is equal to 3 in this formula. You'll get the answer as minus 2 minus 2j. So all in all, you get all the values of x of k, the first one being 6, the second one being minus 2 plus 2j, third one being minus 2, and the last one being minus 2 minus 2j. And now let's look at the second method of finding DFT, which I mentioned using the Twiddle matrix. This Twiddle matrix is basically varying n and k, just like we did in this. We sum n values from 0 to 3 for k is equal to 0, 1, 2. So this is a two-way matrix where we vary n from 0, 1, 2, 3 and k from 0, 1 to 3, and we write down the value of the Twiddle factor. So the 4x4 Twiddle factor looks like this: 1, 1, 1, 1 the first row, the second row is 1 minus j minus 1j, the fourth row is 1 minus 1, 1 minus 1, and the third row is 1 minus 1, 1 minus 1, fourth row is 1j minus 1 and j, and you multiply this with x of n. The rest of the process is pretty simple. You take up the first row, multiply it with the first column and subsequent elements, the first element of first row with the first element of the this column, first column, and then 0 into 1 is 0, then 1 into 2 is 1, 1 into 2 is 2, 1 into 3 is 3. So sum them up and you'll get 6 as the first element. Similarly, if you do second row with first column, you'll get -2 plus 2j, and multiplying, adding, you'll get -2 and -2 minus 2j. So all the elements, they're going to be the same, like this. So once you've gotten x of k, you can write down the values of x of k. You will get 4 values of x of k, because the number of samples that you have in the discrete time domain signal is also 4, so you get 4 here also. From rectangular format, you need to convert it into polar format. If you have any trouble converting this into polar format, you can do it through calculator. I've made a couple of videos, you can look them up. For example, this -2 plus 2j here, it is represented in a plus beta I format, where the magnitude is root of a square plus b square, and the angle is tan inverse b by a. So this becomes 2 square plus 2 square, which is under root 8, and tan inverse 0, so which is 0 here. So that's what we want to do here. So we convert everything into polar format so that we get the magnitude and the angle, magnitude and the angle, magnitude, angle, magnitude, angle. And this is going to be required to draw the magnitude plot. X of k is magnitude. So at sample number 0 it is 6, sample number 1 it is 2.8, sample number 2 it is 2, sample number 3 it is 2.8, and the angle at sample number 0 is 0, sample number 1 is 135, sample number 2 is 180, it will go up, and minus 135 at sample number 3. So that is how you plot the magnitude and phase plots. And a typical question would look something like this: x of n is transformed into x of k, where the number of samples are the same, and you can do it using this method or this method, whatever you prefer. So I hope this tutorial was of help, and this was a basic tutorial of finding DFT. We'll do some more typical numericals in the next video. Till then, take care and bye bye.